Okay, hi, and welcome back. Another little video here. It's a little tutorial on problem solving. Sorry. This is Night Solves Chemistry. It's Thermo problem solving on Hess's Law. That's where we're going with this first video on problem solving series, Hess's Law. Let's get right to it. All right, so first problem solving series is heats of reaction, which just means enthalpy of. So don't be dismayed, don't be disillusioned by the word enthalpy. Enthalpy is just a fancy word for heat. It represents that H, it's that H value, which can also be represented by the letter Q. Okay, Hess's Law. We're gonna do a little practice problem on here on solving some Hess's Law problems. You might notice it familiar. Anyway, more problem solving can be found on the Hess's Law slides, which I'll get to in a moment. But first, our goal and strategy before we start on Hess's Law is that we're going to rearrange and manipulate. So we're going to, let me just highlight those as I say them. We're going to rearrange and manipulate. That means multiply, flip around, whatever, provided reactions, the given reactions that is, so that they add together to exactly match, usually a third, but bottom line is it's a target reaction. So basically I'm going to refer to these as reaction 1, reaction 2. Those would be the given ones, and the target reaction. So I'm going to refer to those as we go through here just to make sure we understand. We want to match the targeted reaction. Now, that's our strategy because our ultimate goal is to do those same things to the heats of the reactions to add up to find the target reaction's heat. That's kind of the ultimate goal. It's finding the heat of a reaction that using given or provided reactions that can be added together. Summation is the fancy term for it. Okay, good. So principles to follow here is that reactants, no matter what, will in fact add to reactants. Products add to products. Reactants, though, that are on the side of reactant side of some reactions and the products of other reactions will subtract from things that are on the product side. You're going to see this when we get to it. These principles hold true. Then step 4 is whatever is done to generate the matching target reaction gets done to the addition of heats of the given reactions. So let's just dive right into a sample problem. Bottom line is we're going to take these provided reactions, we're going to rearrange and manipulate them. Call this reaction 1 and this reaction 2. We're going to rearrange and manipulate those two given reactions to get to the target. That's our target reaction. It's going to match the target. Whatever we do to manipulate these two given reactions, we're going to also do to the given reactions heats, and then add those heats together too to provide the delta H of this reaction, which is not provided, right? This is the whole strategy of Hess's Law, is that we can use two reactions to find a third. Now, why? Well, normally the third or target reaction is not attainable, you can't do it in a lab setting, okay? You can't simulate this lab, so we have to simulate it using things we can do in a lab. These would be two examples of lab-related reactions that we can accomplish, and so we're going to use those to predict the outcome of the heat of the other reaction. And this is good for applying joint reactions. We could do sequential reactions and reactions that we want to lead to a chain reaction that eventually produces the ultimate net result of the third reaction, the target reaction. So this can apply to industry as well as using other reactions that we know how to do. It's causing them to happen in the same reaction chamber simultaneously, chain reaction, products move to the products and then generate the next summated thing. Anyway, let's just get straight to it. So we have reaction 1, we have reaction 2. First thing, look at the target reaction. We'll just start with the beginning. We notice that two FEs are in the reactant side. Well, do you notice 2 Fe anywhere in the two given reactions? You'll notice that there is an Fe on the product side of reaction 1. Therefore, it's on the product side, but on the third target reaction, we need it on the reactant side. So we're going to manipulate, remember our goal is to manipulate these reactions, the given reactions, manipulate the given reactions so that they produce the exact matching third reaction. So if in the target reaction, Fe is on the reactant side, but in the given reaction, it's on the product side, we can flip it to make it match. We're just going to flip it to make it match and be guided by a single reactants at a time, and we'll get there where we need. So we're going to rearrange this reaction, and we're going to write it below number 2. So I'm going to rewrite it with these flipped. What does it mean to flip it? Well, the reaction proceeds one way. We're going to flip the entire thing on its head, put all the products on the reactant side and all the reactants on the product side. We're just going to rearrange it. We're going to flip the entire thing. Okay, which means we're going to write 2Fe plus 3CO2 yields Fe2O3 plus 3CO. So now we have this reaction, reaction 2, and reaction 2, and now we've rewritten reaction 1 down below, and we flipped it over. Now all we're doing is rewriting. This is a simulation. Now that's suggesting, when we flip it, we're suggesting that the reaction 1 is reversible, can be flipped. Now there is some data to come forth in the next unit or next part of the unit, in the kinetics part, that does suggest that reactions are in fact reversible, but that's neither here nor there. It's inconsequential to us. But simultaneously, what has happened, if we flip this reaction that produces a negative heat originally, how would we also flip that heat? Well, we flipped it. It was negative 26, so its heat would now be, of this flipped reaction, positive 26.74 kilojoules. We've got to be able to stay focused on that. So I'm going to shrink this a little bit. Okay, good. All right, now that we flipped the reaction, now we have to see what else we got going on. In the final reaction, we do not have, notice on the reactant side, CO2, but the flipped reaction 1 has 3 CO2s on the reactant side. So we need to add to the second reaction. We look at the second reaction and see if there is any CO2 on the product side. So the way we've rearranged reaction 1 was to match the Fe's in the reactants as the Fe's in the reactants of the target reaction. That's why we did the flip around. But what that's also resulted is in the reactant side, when we're going to add, is going to have 3 CO2s. Wait a minute, there are no 3 CO2s in the reactant side of the target, which means they had to cancel. How can they cancel? Well, reactants can subtract from products. So if we can have, when we add these reactions up together, if there's a reactant CO2 and a product CO2, they'll subtract from each other. And that's what we have. We have 3 CO2 and a 1 CO2 right here. Understood 1 coefficient. Well, 3 minus 1 is still going to leave us on the reactant side 2 CO2s, which does not exist in the target reaction. So we need to come up with another alternative. How can we subtract? How can we make it so that we can subtract 3 from 3? How do we get 3 CO2s in reaction 2 to subtract? Well, we would need to multiply the entire reaction. If we were to get a 3 coefficient from that CO2, we have to multiply the entire reaction by 3. I actually want to erase this 2 there. Okay, I know it's reaction 2, but I want to multiply the entire reaction by the coefficient I desire, and that's going to place it into everything. So we distribute that by doing a 3. 3 times 1/2 means 1 1/2, and then a 3 CO2s. And now, when I add these things up, you'll see what seems to happen. Okay, so first thing, when I rewrite this down on the next thing I suppose, when I rewrite these down in the addition form, I can see that there are 3 COs on the reactant side, but also there are 3 COs on the product side of the other reaction. Those will thus cancel. Let's actually copy this so I don't lose the progress of this problem. Okay, so we see once again 3 COs on the reactant side here. There are no COs on the reactants of the target, but I notice there are 3 COs on the product side of the second rearranged first reaction. So if it's on the reactants and the product side, they can cancel. 3 COs, they subtract from each other because, you know, a product is a negative reactant essentially. All right, and so 3 plus a negative 3 CO2s subtracts them out. All right, then we have, add straight down, we have 1.5 O2 and 2 FEs. 2 FEs plus 1, oops, it's 1.5. 1 plus sign, 1.5 O2 yields, wait a minute, I have to, the FE goes brought down, this gets brought down, but the 3 CO2s on the reactant side, there's also 3 CO2s on the product side, so those cancel, and that leads to no, this doesn't bring a product at all. This was brought down already. This was canceled. That leads to this being brought down, Fe2O3, and that is our final product. And by the way, that exactly matches our target. We've accomplished the mission out there. We manipulated reactions to match the target reaction. But our job is not done. Because what we did to the reactions, remember, whatever we do to generate the matching reaction, we must do to the heats when we add them up. We already did it with reaction 1. Reaction 1 had a heat that was negative. We flipped the reaction, so the heat became positive. Reaction 2 was negative 283. We tripled that whole reaction, so the heat also gets tripled. 3 times 283. So then over on this side, we have the delta H equals 3 times negative 283. And I'm not going to insult you there. 3 times negative 283, and these are all added together to plus 2674 kilojoules. You should get a negative amount of kilojoules. And I guess there's something wrong if you refine this. There'd be some sort of negative amount of kilojoules. If you did your math here, it would mean if it's negative, that just means released. And so if the answer choice does not offer you a negative, we can assume they mean release, and then you can just choose the answer even though it doesn't have a sign attached to it. So that's a Hess's Law problem that solves us for this. Oops, excuse me. And more problems exist in the slides. The extra bonus slides for kinetics is the Hess's Law slides in there. So go take a look at those if you want to see some other sample problems as to how they relate. If the slides don't transition right on Google, then of course I want you to let me know so I can fix it and give you maybe the PowerPoint setup instead. So those practice problems are present in the extra bonus slides that I attached to the day 3 videos, Thermochemistry day 3 videos are posted on Google Classroom. That concludes the problem solving segment for Thermochemistry Hess's Law. Get after it. Let me know what you got, and let's go get it right. Go Dogs.